In fact, I gave a bit similar but not identical talk about a week ago in Rikyo in Tokyo, and somebody maybe George was present here. I apologize, but yeah, but it will be not really identical. It will be a bit different. Yeah. So first I'll talk about just to explain the whole story. I need to make some first explain finite dimensional situation. So it's maybe kind of first paragraph will be about Lefschetz symbols. Okay. So we start. Let's X will be algebraic manifold over complex numbers of certain dimension n. And then we have a function, which is a section of structure shift, which we interpret as U as a map from X to a affine line, or you can see just C, kind of polynomial map. And suppose we have a volume, some top degree form, which I denote by volume. It could be principle degenerate. It's a section of the line bundle of forms of top degree. And we have the story, and we want to study integrals exponent minus function divided over h bar times volume over certain non-compact chains gamma such that integral is convergent. Yeah, so we have studied such function. H bar is a parameter. So I'll make some simplifying assumptions. Just really to simplify, everything works in complete generality. First, I assume that f has only I have isolated critical points, and because it's algebraic, there are only finitely many of them. Let's go to b1, bk, x, so that derivative at its point is equal to 0. And second, all critical points are holomorphic Morse kind of points, which means that near each pi there exist local coordinates. Let's call it x1 up to xn, such that function is equal to some constant called zi plus x1 squared plus x squared. It's actually coordinates are analytic, not algebraic. And the I is in C is a critical value. And maybe the third point, I will assume that there's no critical points at infinity in sense. Which means that the only change in topology of fibers is local near critical points. So you cannot remove something at infinity and add to some fiber. Fibers is near pi, but not at infinity. So near pi, you kind of one fiber is kind of singular, the nearby fiber is looks like this. Okay. Later I will assume it. Not now. Okay. Integrals There are kind of two cohomology series, Betti and de Rham cohomology, like in usual brake geometry, kind of the twisted de Rham cohomology. It will be complex of sheaves. I consider complex of sheaves, and this differential will be d maybe minus df divided by h bar. I get this twisted complex. What is the meaning of this differential? It's d minus df h bar is exponent minus f of h bar d. Yeah, so it means that if you consider forms multiplied, algebraic forms multiplied by exponent minus f of h bar, then after rescaling the differential became this one. And then we'll consider one can put following effects. That first, it's if consider hypercohomology of X in the risky topology with complex of sheaves. This hypercohomology is 0 under my assumption if I'm not in the middle dimension, and isomorphic to C to power k, where k is number of critical points, if I is equal to n. So in this case, all cohomology will be concentrated in middle degree, equal to number of critical points. And now what are, and in particular, we have this volume element. Which belongs to its element of this nth hypercohomology. You don't really go to hypercohomology because it's obviously killed by differential. It's the very end of the complex. But this class depends on h bar, because cohomology depends on h bar. Now, what are cycles of integrations? And now I will explain the following. Pick theta in R mod 2 pi z such that there is no I non-equal to j, such that the I minus the j it belongs to yeah, so theta is not angle of direction connecting two critical values. Then just fix the theta. Then I claim that for any critical point, I have a certain integration cycle, which I denote by cycle depending on I and theta and the theta. What is this cycle? I consider in my plane of values, I have some other numbers. I have point zi, and now draw a ray with direction theta. So the ray zi plus exponent theta in positive numbers, as you can see. Because of my assumption, there will be no more critical points on this ray except critical value on these points except the origin. And near the origin, I just repeat my picture here. The fiber of the origin will be singular hypersurface given by sum of square equal to 0, and then it's kind of opened nearby. And what one can do, one can draw. It's not canonically, but up to isotropy, one can draw a sphere, very short sphere. It will be a vanishing cycle. And then one can make just choose sphere in a smooth way in a fiber along points of this ray, because the bundle is trivial on a ray. It's locally trivial and the ray is contractible, so all fibers are diffeomorphic. You can move it, and you get this. And here to the projection by map F of this symbol. And fibers are spheres. Maybe except point Z, we get a point. So this left symbol, you see that it's kind of one parameter family of spheres. It's diffeomorphic to Rn. N is a complex dimension. Now we get this in non-compact chain. And now which integrals will be convergent? One should be a little bit careful with the size of these spheres, but in general there's no trouble. And then the integral of exponent minus f of h bar times volume over this symbol is well defined, or in fact it's convergent, if argument of h bar is sufficiently close if this f bar over h bar, a real part will go to plus infinity, which means that argument of h bar lies in the interval theta minus pi over 2 theta plus over pi. Okay. So we get, so it means that we get function in a holomorphic function in a half plane. This integral will be a holomorphic function in half plane with direction theta in variable h bar. And we get several functions depending on our rays. Yeah, in fact, one can show that this theta I can be extended to functionals on this hypercohomology and the form a basis. So again, kind of fact. Defines a functional of this hypercohomology to C, and they form a basis of dual space. Okay. Now I might make just a couple of further assumptions. They are really pretty innocent. The first assumption that I assume that critical values are distinct different points, and maybe 5, even stronger property that no 3 critical values lie on the real line for any I non j non k. Are not kind of arcolinear. Yeah, so this situation is kind of forbidden. Okay. Oh, maybe I 1, I 2, I 2, 1, I 2, 2, 3. Because k is the total number of my top points here. Yeah, right. Yeah, under these assumptions, I have kind of, I have k times k minus 1 forbidden directions. when my Lefschetz symbols are not defined. We can have something like this. It's called Stokes race in Stokes race, and if you pick theta outside of Stokes ray, then you have a locally constant family of integrals. So you get essentially k times k minus 1 interesting holomorphic functions defined each in its own half plane, and also depending on point of integration. The question is how they function depend if you cross the ray. So suppose I get kind of theta is equal to sigma j. It's kind of argument of zj minus zi. And I get maybe theta plus and maybe theta minus two closed directions. So what will happen in my picture? I get points whatever zi and zj, and for theta plus, I put this race in a z-plane like this, and for theta minus, I put them like this. So from this, you can see the following. So the claim is this function I forgot to make notation. I denote this function by I e sigma of h bar. This will be my integral, and the claim is the following. It's alpha j sigma minus is equal to alpha j sigma plus on, I mean, it's defined in slightly different half planes. It's on common domain of definition. Okay, maybe for argument h close to sigma. It's the first thing. It's obvious because this path just moves continuously and you see the same integral. But second is that I just of sigma minus is equal to I of sigma plus certain multiple. Yeah, I've considered this two chains. You get certain number Nij multiplied by Ij, whatever sigma plus or minus, doesn't matter because it stays the same. Why so? Yeah, it's kind of elementary topology. One can see that if you consider some relative homology group in the neighborhood of just if you consider such domain and put its kind of homology relative to take pullback and take homology relative to this preimage of this part, then the homology will be two-dimensional in degree n, and this will be one basis, will be another basis. So it should be some upper triangle change of transformations. And maybe I could say what is topological meaning of number Nij. It is certain up to sign intersection number of two cycles which intersect properly, namely consider sigma I of theta plus intersecting with sigma j of sigma minus plus pi. So what does it mean in my picture? I have zi, zj. I consider a symbol which projects to this ray, and another symbol which projects to this ray. It's kind of opposite to what I draw for sigma minus. And the intersection will be compact. It will be two compact spheres intersecting in a fiber. This numbers also Nij, Nji. Its matrix is kind of symmetric, anti-symmetric. I was a bit not careless about choice of these symbols. To make it orientation, I also should choose orientation. So that's defined up to a sign. All things defined up to a sign, but numbers are essentially symmetric. Okay, just kind of remark, the whole story, everything generalizes to arbitrary pair of X and F, and maybe volume. Instead of critical points could be not isolated, not compact, but what one should do, what one should essentially keep track of, let's set of the I will be defined as a set of points in C, set that F restricted of the preimage of a small disk, radius at Z, is not a fibration, not topological fibration. This set of, it's called bifurcation values, will be finite set. And then you consider something like homology of pairs for some neighborhoods that will be possible, replacing these critical cycles. And these numbers Nij will be not numbers but matrices, rectangular matrices mapping from one space to another space. So that's essentially the same story. And also 3 points can lie on one line, and that. So it's now second paragraph is resurgence. Just turn blue. I have these integrals, I sigma theta. And if h bars goes to 0, there will be certain kind of leading term in this integral. The integral will be essentially concentrated near origin when h is equal to 0. When h bar is 1. Yeah, so we can write its exponent minus zi over h bar. Then it will be, because the volume of a sphere gets something like h to power n over 2. And then you get certain the rest term which I denote by E sigma, kind of modified of h bar. And this thing, the rest admits asymptotic expansion. As h goes to 0, it will be certain sum. Maybe small n h, and goes to 0 to infinity, h to power n. So this is asymptotic expansion, it's form of power series in h bar. And in general, it's divergent. Yeah. Now, so our functions defined only in a half plane, so it's there's no reason for this to be convergent. Now we have this jump formula. What happens with my original functions if we grow from one Stokes sector to another? Again, also get sigma j, get sigma plus, sigma minus. And if you apply to this, see what happens with modified series, then we will see the following. So the jump of ij modified is 0. Delta means jump, how value for theta minus and sigma plus depend. And jump of delta I modified will be the following. This h to power n of 2 is the same. It will be exponent minus zeta j minus zeta I divided by h bar times maybe nij times delta j modified. So you change your function by adding this function, and this has zero Taylor expansion at h bar goes to 0 when this real part of this thing is positive. Yeah, so it's very fast decay. So it doesn't change this asymptotic expansion in the half plane because it's convergent here. Doesn't change this asymptotic expansion, so this means that C n I h bar is actually something depending only on I, not, oh, sorry, maybe I put theta. Because it's theta. So the series doesn't depend on the choice of sector. So I get plenty of series, and so the claim is the following: for any I, formal power series, maybe I call it something like sigma I, which is sum over this coefficients C and I e to the power n, is resurgent. What does it mean it's resurgent? We apply formally what's called Laplace transform, sigma I. We get series in another variable which is denoted by S, which will be sum over C and I divided by n factorial S to the power n. Just divide by n factorial, is convergent for at least neighborhoods of 0 and admits endless analytic continuation. What does it mean admits endless analytic continuation? It's one can make some very general notion, say that if you have a germ of analytic function in one variable, then there exists a countable set, so that for any path excluding this countable set, the function in static and domain convergence, the function admits analytic continuation along this path. But here it will be something much more elementary. In fact, one can write the formula. What is L sigma I of S? Why it admits endless analytic continuation? The easy calculation shows the following. This function is d over ds to power n over 2 minus 1. Yeah, so it's, let's here for a moment assume that capital N is even, so it will make perfect sense, of the following function of S, of kind of function which obviously admits endless number of continuation, of function S goes to integral over kind of vanishing sphere in a preimage of point Zi plus S. You integrate the form which is volume divided by df. You get volume form on the fiber and calculate volume of sphere. If you move around, the cycle will admit some monodromy by kind of Picard-Fuchs equation, and you get an endless number of continuation. And what is good for? This property of this being resurgent, you can from this formal power series and for generic theta calculate this integral. You get something like sigma, whatever, up to of h bar is equal to 1 over gamma n over 2, maybe exponent minus 0 h bar, and you integrate and make certain integral from exponent of square root minus sigma times r plus exponent minus s of h bar, and integrate times this. I make kind of double integral. You make its antiderivative n minus 2 over minus 1 times, which is this integral, and then make Laplace transform. Get this function. Okay, yeah, so I explained you finite dimensional story. Now go to infinite dimensions. But you still divide form by df. It's in numerator. Yes, it's just arbitrary closed form. Yeah. Just arbitrary of degree form. Sorry?
The kernel is Laplace transform in h bar.
1 over h bar, yeah, kind of.
Yeah, so the kernel is s h bar, not s over h bar. Right?
No, it's you take it's like 1 over. It's like Fourier transform. We put 1 over h bar as a. Yeah. Where?
From sigma I to Laplace transform sigma I.
You we divide by n factorial. No, this is formal transformation with power series, in which you can imagine that you. Sir? Inverse Laplace transform. Yeah. Yeah. So it was kind of very slow introduction. I apologize to it, but now I'll go to first interesting case, kind of infinite dimensional exercise. Yes, with heat kernel. Yeah, this seems to be really new. Yeah, so start with some first C infinity Riemannian manifold. Maybe complete. Yeah. And pick 2 points in this manifold. And now I will assert some infinite dimensional manifold. X will be infinite dimensional manifold. Kind of, it's again, real manifold. Not complex one, and I denote by it's by XR to say that it's real manifold, which will be the set of paths in connecting my 2 points. And I defined a function of the path, which will be the usual Dirichlet action. 1/2 integral from 0 to 1. It's called the coordinate t. What I have d phi over dt. I take square times dt. And by this, I mean kind of use Riemannian metric. Sense. So it's the square of length of tangent vector. Now maybe I remove this part. And we want to integrate exponent minus f d phi. This is Feynman integral. It's f is maybe denoted by action, if you prefer physics notation. So we want to calculate this pulse integral, and we kind of know what is the value of this integral. It's a matrix element of a heat kernel. You can see the exponent minus Laplacian of my manifold, and I just use physics notation to be kind of, you can see the heat kernel is integral operated, so it's some density associated to 2 points, maybe delta y0, delta y1. Okay, so that's pretty obvious. But now we want to integrate over h bar, divide over h bar. So we integrate exponent minus f b over h bar d phi. And the claim is, again, it's kind of not mathematics because it's kind of formal manipulation of the infinite dimensional story. The claim, it's a matrix coefficients of heat kernel, but with time h bar. Yeah, so here's something really funny. You get h bar in numerator and denominator. How it can happen. And the reason that if you look on the action, you can see the action functional. You see that it time appears in degree -1. And if we multiply it by h bar, it means that we can rescale time, and it will be maps. It will be maps of maps from interval of 0 h bar to y, and 0 goes to y0, and h bar goes to y1. And we again integrate this usual so in such kind of rescale time, you get the same formula, but for maps from short interval. And then by general rules, it will be heat kernel for smaller time. Yeah. Now, so what this has to do with my previous story? I can make a conjecture which is kind of vague. I don't really know precise way to formulate it. Suppose y is maybe connected component of r points of certain variety yc, of algebraic variety yc defined over real numbers. So we can complexify all my coordinates. And metric extends to algebraic tensor, algebraic section of maybe cotangent symmetric square of cotangent bundle to yc, kind of algebraic metric. Then this integral then we should have this picture with resurgence and all the story. In particular, this heat kernel. We write as exponent minus, yeah, so it'll be leading term, when h bar goes to 0, then what we'll have here, the dependence will be length of distance between, for shortest geodesic, between points y0 and y1 squared divided by 4h bar times some kind of series in h bar, which should be resurgent. And when you make this analytic continuation, you will see kind of other critical points. You will see complex geodesics, lengths of complex geodesics in this. Complexified manifold. Yeah, you'll see just this whole story in the moment. Kind of the best example is y is a hyperbolic plane. H2 is usual hyperbolic metric. Then consider heat kernel. Heat kernel depends only on distance. Because it's a symmetric space. And then this integral, which I denote by maybe I0 of h bar, this heat kernel, and maybe at rho, will be the following. It will be 1/2 h bar to power 3/2. H bar is the time, and then times the following integral from s equal to rho to plus infinity, exponent minus s square over 4h bar. Yeah, s has meaning of like distance divided by 4 bar. Now integrate by it's kind of some standard formula by McKean, I think first discovered maybe 60 years ago. Okay, so you get this formula and you integrate. So how one can see this formula? Yes, this term will be completely innocent. I will completely ignore it. What happens with the integral? I just on complex plane, I draw point rho. When this thing vanishes, but also it vanishes in rho plus 2 pi I, rho plus 4 pi I, and so on, rho minus 4 pi I, and also at point minus rho. Yeah, so you get kind of two sets of kind of bad points, and the path of integration is like this, yeah, from 0 plus infinity. And in fact, hyperbolic cosine is even functions, function of s square, to go to the variable z, which will be s square over 4. It's a path of integration. Where we integrate from rho to plus infinity. Yeah, and instead of, it's better to go to new variable z. So the integral And I introduce for any n for any n in Z, I introduce the integral In of h bar. Again, it will be the same beginning. And now integrate from S Zn I just change notations. S square O phi denoted by Z, so it will be dz. And these things in denominator, I denote 1 over square root of things in denominator, but I know about phi rho of Z. And what is this function? So now I will go to Z plane. It was kind of S plane. Now it will be Z plane. And in Z plane, we draw the following things. So we consider some parabola, and then on parabola we get a bunch of points. Corresponding to number n, 0, 1, 2, and so on. So we get kind of maybe denoted by Z0, Z1, Z2, Z3, Z minus 1, and so on. We get these things, and we get a function, phi rho, its function, it's kind of doubly ramified. At point Zn, of these points like on a parabola. And what we integrate over such things, such directions. And what I claim that from this picture, one can see some kind of this wall crossing formulas which I have before, but with finite infinitely many critical values. Yeah, in fact, I want to say that Zn is square of length of certain kind of complex geodesic connecting y0 over 1 with some binding number square over 4. So it's exactly the action over some complex critical points. So what is roughly the picture? This hyperboloid, it's like sphere with imaginary radius. And you have a sphere, and you get 2 points. Then you have different geodesics. You can go straight, or you can go once or twice, and so on. So you can turn around several times. And then you get the square of this number, which is, you get to row this square of n times wind around, you get, but it's imaginary, you get 2 pi I, so you get complex number. And for example, with this picture, it's very easy to see what happens if you start to rotate this theta. It's kind of secretly, here it's kind of theta is equal to 0. This corresponds to direction with slope 0. But if you start to rotate the whole story, let's do it like this. You get maybe another 2 points, another 2 points, another 2 points. You choose some theta which is going in this direction. There's a claim that this cycle corresponds to this yellow line is again is equivalent to the following sum. It's equivalent it's pure topology. It's equivalent equal to this cycle with multiplicity +1 plus this cycle with multiplicity +2 plus -2 -2 +2. Yeah, yeah. So it's purely a property of this doubly ramified picture. One can make easily exercise if you draw this cycle, then it will be homotopy equivalent to some of this cycle. So you get some simple formula how this basis for Lefschetz symbols change if you rotate your theta. Yeah, you make a new theta and draw this Lefschetz symbols from whatever space in direction theta. I claim that this corresponding integral will be equal to sum of integrals when h bar still lives in common intersection of common half plane of these original guys with certain weights. Because yeah, for example, let's do a really simple exercise. We get kind of why if we have first -2, because when we draw this cycle, yeah, one can say the following: it's equivalent to this plus this, but then it will be equal to just one can kind of again replace by this +1, and now put it with -1 because here we start from wrong sides. Its monodrome is -1. It takes square root, so it will be equal to this -1. And this guy is equal to this cycle again minus this cycle. Because I can kind of close here, you get so you get this -2, and then I continue by induction. So you get this +-2 rule. Fine. Yeah, but then there's something very dramatic will happen if you start to go to a direction close to negative degree. But it's still everything works, and one can do the same story for S2. When manifold is S2, instead of hyperbolic space, what will happen? You just it will essentially the same picture, but now I should apply the formula. You have the same formula, but now make it rho equal to purely imaginary E times angle distance, because one can say the sphere is hyperbolic space with imaginary kind of imaginary radius. Yeah, it's the same story. And also just change z to -z, kind of rotate action to minus action. And what will happen here? It will be the following picture. If you kind of get point 0, yeah, if now consider rho is imaginary number plus 2 pi n squared, take divided to 4 and take minus n, we get numbers something like this. And you imagine that all things shrinks and goes to real positive hyperbolic cosine. For spheres, it will be usual cosine. Yeah, just you take the same function, put rho will be imaginary number, and put s. No, I just have the same function of z. Take function of minus z. Yeah. Yeah, it will be automatically because s is square root of z, so you get cosine. Yeah. Yeah, just get this literal function doubly ramified and the things. But now the situation is different, and what we have here, it's, if you kind of have the shortest distance between 2 points, it will be shortest distance on a sphere. Then you see that it's, if you make this Lefschetz symbols for theta equal to 0, it will be not well defined because it will be things with even smaller, larger values action. It should kind of rotate only sigma a little bit, goes to one half plane or to another half plane. You just the things were really for sigma equal to 0. Now it's Stokes in Stokes ray. Now, for example, this guy will be square of smallest length on a sphere. When you have two, shortest geodesic between 2 points, yeah. And the whole integral which we are taking off, it looks that we integrate over a cycle which surround the whole thing from both things, which you can decompose at certain linear combination of Lefschetz symbols for sigma plus or for sigma minus, and then you get the same Stokes phenomena. Yes, yes. So essentially, for hyperbolic space, if you go Stokes kind of Stokes things in a negative direction, you get the situation of a sphere, roughly. Yeah. So it's all looks pretty satisfactory, and one can see all from this point of view. One can see all topology how what are intersection numbers of the Lefschetz symbols in infinite dimensional situation. No, intersection numbers I have. Why not? Because it's the cycles of half infinite dimensions that intersect in finitely many points. Yeah, one can, no, there are many exercises to do here just to check what are Lefschetz symbols. There will be solution of some parabolic equations. And then it will be some kind of number of some instantons and certain. Yes, yeah. No. But I claim to see that at least on level of formulas, it looks like we get exactly perfect example of this resurgence. Yeah. Here we are kind of lucky because it's case of integrable system. We know exactly the spectrum of Laplacian and so on, length of geodesics. But I claim it should be very robust. It's if you make some polynomial metric, that will be the same property, which will be both sides are hard to calculate, but there will be. Okay. Now, kind of next paragraph will be about dependence on parameters. So it's kind of very simple situation. Again, first consider finite dimensional situation. Finite dimensional case. Suppose I get not one, I get some bundle for some total space to some base, and I get some f total to C. I get a map where fibers called XB are algebraic varieties. Over C, and functions are restricted to XB is a polynomial map. For parameters, I don't assume that it's holomorphic, just continuous family of parameters. And now I have also, suppose I get a volume element and so on. But in all my story, if I integrate integrals depending on parameters, what I explained you is that this was kind of before calculating integrals, we have the following thing. We get kind of functions in C, and we get some numbers n, aj, also depending on parameter in Z. And also I assume that function sits for any b, say, is only Morse function. And so holomorphic Morse. Just to simplify that. Yeah, it's the same assumption with all different eigenvalues. But I don't assume, assume that they are not collinear. Yeah, at some point will be collinear. Let me draw the picture. Yeah, so there are kind of walls, real walls in parameter space. A wall appear when 3 points, zi1, b, zi2b, and zi3b. No. No, they're all distinct. Zi not equal to zj. Suppose they're all distinct, yeah, but I don't assume that don't like not collinear. And walls appears when the whole things will be collinear. It's effect of codimension, real codimension 1. And if we cross the wall, when we're outside of the wall, these numbers n, I, j stay constant. But they jump a little bit when jump across the wall, and kind of, let's say, before the wall, before crossing, we get my points, let's stay something like this. And after crossing the wall in parameter space, the triangle will be arranged opposite way. Yeah, so it's get going to be zi1, zi2, zi3. And here I get some numbers. Let's denote numbers by something like before wall will be n, 1, 2 minus, because it's before wall 1, 2, 3 minus, and 1, 3 minus. And here get 1, 3 plus, and 1, 2, 3 plus, and 2, 3 plus. And then there is kind of things which, of course, was known in some way, but it's kind of Chikoty-Vaur formula for transformation. It's Picard-Lefschetz, yeah. Yeah, it's, maybe I should say Picard-Lefschetz formula, yeah. Yeah. Yeah, it's depending on who are your hero. Yeah, okay. Yeah, but heroes, yeah, no, in fact, it's Lefschetz, yeah, maybe, yeah. Then the claim that it's n1, 2 plus is equal to n1, 2 minus, n2, 3 plus is equal to n2, 3 minus, but n1, 3 plus is equal to n2, 1, 3 minus, plus, again, maybe minus, because I was kind of sloppy with choice of orientations. It's changed by product of these two things. And which is very nice. It means that if you have a family of integrals to study, not one integral, but family of integrals, you should study a continuous family of connected family of integrals. You should calculate these numbers nij only on some specific value of parameters. Then by these things you can formally do it for any other values of parameters. So it's very convenient property. Now I'll just say that make its infinite dimensional illustration. Example of how one can apply these parameters and the whole story. So I'll start. What will be the data for this infinite dimensional model? Y will be some complex algebraic variety, manifold. Then I'll have L in cotangent bundle. It will be smooth closed Lagrangian submanifold, and I assume it's exact. And exact, what does it mean exact? Over C, yeah, smooth algebraic, yeah, kind of. It's kind of algebraic variety. And suppose it's exact, means the following. If you consider kind of natural form PDQ on cotangent bundle, restrict to Lagrangian should be equal to differential of some function. So we have additional Cherenkov function. Now, what will be parameter space? Parameter space will be Y itself. And now what will be infinite dimensional manifold? XB, or maybe XY. Y is in Y. Maybe the same as point B in the previous notation. XY will be the space of infinite dimensional space of, again, paths from map from 0, 1 to cotangent bundle. Now such that phi of 0 belongs to cotangent fiber at point Y, and phi of 1 belongs to L. Now, so what's the picture is that you have this cotangent bundle, you get this whatever L, you get cotangent fiber at 0, and you're interested in some kind of path connected one to another, parameterized path. Okay, and the function f, fy of the path phi, will be the following. You integrate form this PDQ, which I denote from 0 to 1, and maybe at up to sign, you take f of phi of 1. You get this functional. I don't want to say yet what is the integral, but let's apply this critical points. Critical points are constant maps from interval to intersection of L with cotangent bundle. You get constant maps will be critical points for this functional. Now one can start to, I don't know, or either to apply Chikoty, this Picard-Lefschetz formula, and want to see what are these numbers. Yeah, for some values of y we had problem because maybe critical values coincide. We should remove them, and or the intersection is non-transversal, and we get something. We get on y cross C star, which H plane, minus some walls. We get a bundle of we get realized bundle. Basis will be intersection points. And then if you cross wall, you change the basis by some upper triangular matrices with integer coefficients. Cross wall get apply kind of matrices with some Nij. And Nij have kind of complicated meaning. You can see the path in the space of path. Because it depends on parameter. I told you that this Lefschetz-Stimpels form basis of some homology theory associated to the function. If you remember those the rank homology, those form a basis. And if I change the wall, I kind of change the basis. That's how I. Yeah. Oh, you get, yeah. finitely many points you have. In this case, we get only finitely many points because critical points are maps to intersection points which are finitely many. It's algebraic varieties. The intersection is finite, transversal, that's finite, yeah. Yeah, so you get kind of, this cohomology will be some bundle, and what you glue some vector bundle on a parameter space, for example, on Y itself. One can make some simple exercise, for example, take Y is equal to C and H bar equal to 1, kind of specify. What will happen, it's pretty funny story. You get maybe algebraic function on one variable. F will be, L will be curve in a C square, and we'll get function here, which will be interpreted as multi-value function on one variable. And then you start to draw certain pictures. It will be ramification points. You get triple.
No.
Yeah. One can, for example, in the case in Y equal to C, yeah, is the example which you gave as example on your talk. You probably should, yeah, you should know it. Yeah, yeah. But the story is pretty funny. You get kind of like finitely many points. You start to draw some diagram and put some numbers like 1, 1, 1, maybe 2, 1, and yeah. So you start to draw certain finite diagrams with these numbers n and j appearing here and there, and it will be finite, interesting picture on a plane, which allows you to glue some trivialized vector bundle by some upper triangular matrices to some vector bundle. So you get vector bundle on C, but also this vector bundle will be automatically endowed with some kind of natural Stokes filtration, because it will be correspond to take different real imaginary parts of the story. I do not want to go into the details. It's at the end of the day, one can construct a Stokes data over integer numbers for some irregular holonomic D-module. Yeah, and in general, what I expect that in not in case of one dimension, that I will associate with L, such L will give certain canonical holonomic D-module with irregular Riemann-Hilbert correspondence associated to L, and this can be compared with the following story. Yeah, there was a paper by Christopher Dodd a few months ago. He constructed canonical D-models, assuming that H1 of L is 0. He constructed canonical D-models, solving a conjecture of mine that should be some canonical D-model associated to things. And he constructed using reduction to characteristic P's, stuff like this. It was a different story. But what I conjecture that it's, for example, in this case, this D-model should be not only just D-modules, but it should be exponential motivic, should be given by some Picor-Fuchs equation and also introduce exponents somewhere in the game. In particular, Stokes data should be defined over integers, so you get some integer lattice. And here, this transcendental construction of this integer lattice part of the story, which confirms the general expectation that it will be exponential motivic. So it's still open question that you get exponential motivic. But here, these transcendental constructions with gluing produce the whole.
Is it D-module on Y?
On Y, yeah. D-model on Y.
In case Lagrangian is the graph of
exponential of the function, yeah. But if it's not a naive exponential of algebraic functions. It will be something else. Yeah, so that's kind of short illustration about dependence on parameters. There are a few more things which we can add. This is game. Maybe one short paragraph will be closed one forms instead of functions. Suppose I get, again, first start with finite dimensional situation, get finite dimensional variety. And if I get a function, and suppose I get one form of y which is closed. If you have a function, then the form will be df. Then the twisted Ram complex is again defined. We just consider omega is differential d plus beta divided by OH bar. So it's perfectly defined, and the story is the following. If one it doesn't make sense, one can again speak about critical points. Will be zeros of my one form, and we'll also speak about like Morse critical points and so on. And one can also make kind of Lefschetz symbols. Just draw things on a universal cover, maybe a billion cover. So you get certain symbols, but now there could be everywhere dense on my original manifold. For example, if fx x is a let's say curve, you get one form, then what we draw a kind of trajectories of holomorphic foliation of quadratic differential. So it could be everywhere dense curve. But on universal cover gets still nice convergent integrals, and you get the same story. So what I think it's not defined because we don't have value of function, but I modified is well defined. Because I modified, you divide by some power of h bar, depends on the dimension, but also modify by critical values. So you kind of make function choose f on universal cover so that f at critical points is equal to 0. And then it makes the integral so kind of normalize the form like this. And the simplest example is x will be c minus 0, c star, with variable x, and one form will be, bit will be 1 minus 1 over x times dx, which you write is a differential function universal cover x minus log x plus 1. This will be kind of function on universal on universal cover. But let's say if x is real for between for x between 0 plus infinity, this function has a minimum at 0.1 and vanishing 0.1. And what we integrate, you get only one critical point, only 1, 0 critical point. X whatever 1 is equal to 1. And the integral modified depending on h bar, and maybe for theta equal to 0, will be the following. It will be 1 over h bar to 1/2. And you integrate This will be Lefschetz timbals. Timbal, this sigma 1, theta. You make this integral of h bar. It will be volume form dx over x. So you make this my integral. And what I see is that we get something like gamma s over s to s minus 1/2 exponent minus s. S is just for convenience notation, it's inverse variable. Yeah, so you get gamma function. So you get after division, you get kind of interesting part in the Stirling formula. And this is again a resurgent series by general reasons. The old story with resurgence generalized to this case of one form. And in fact, this function A1, maybe I called I plus of H bar. I plus of H bar extends to H bar sitting in kind of C minus negative. Because we also can rotate theta, we get half planes, so altogether swap almost the whole plane. So you get analytic function in this plane. So it will be according to when we choose different thetas and we get different. I think we get I minus H bar will be equal to 1 over I plus of minus H bar. It's defined only on this thing. Now for imaginary part of H bar positive, we have the following transformation rule that I minus is equal to I plus minus exponent of minus 2 pi I of H bar I plus. And for imaginary part of H bar negative, I get almost the same formula. And one can understand here all terms in this formula from geometry, from the geometry, namely my variety x is C star is cylinder. Yeah? My variety is a cylinder. And I get only one, this is my critical points, x1. And I have essentially only one on this universal cover, gradient line goes from this point to itself, called class gamma 0. And what has happened here, for example, here get minus 1. This minus 1, it's kind of, it's a get, this class gamma 0 appears with multiplicity minus 1, as there is no multiple. And what is 2 pi I or minus 2 pi I plus minus 2 pi I? You get gamma 0 or minus plus minus gamma 0 appears in multiplicity 1. You get just, and 2 plus minus 1 is integral of plus minus gamma 0 of my form beta. Yeah, so in general, you get integrals of form of going from one, connected 1, 0 to another 0. And here will be integer number, and you divide this by H bar. Yeah, so that's the story about finite dimensions. So now will be almost the last slides, kind of infinite dimensional version. So in general, infinite dimensional version can be placed in the following framework. One take, let's say, again, complex algebraic symplectic manifold. Then you have two Lagrangians. Maybe Lagrangian, let's say first submanifolds. The whole story should be generalized to singular objects as well. And then you consider space X will be space of paths connecting two Lagrangians. And one form, it's kind of you integrate over the path of pullback of two form, and you get one form. You get closed one form. Again, critical points will be constant maps to intersection points. All looks fine, or that one can make whole repeat all the story, and now this new effect will appear, not visible in, not present in finite dimensional case. What is this new effect? When we study this, let's say, gradient lines for one critical point to another and change parameters and so on, what will happen is that sometimes in finite dimensional situation, if you change parameter, you can kind of gradient line connecting two points can break some two gradient lines going to some intermediate points. And it's kind of infinite dimensional case. And if you interpret path as a family of paths, so what happens, the path will be mapped from kind of like 2-1, going between this my Lagrangian L1, L0, and that's what can happen, this degeneration, it corresponds to the fact that paths decompose in two passes. Path in path space, and in case of surfaces, you get this degeneration. But there's another degeneration possible, which is like this, or like this. Which roughly, if you think what happens in the case of path space, it's the situation the following. You get some kind of gradient line, and then at some point it's kind of very fast move, make some loop, return to the same place, and then continue back. Yeah, so it's a new effect. It should be taken into account. And what is the meaning of this effect? Meaning is the following. We get certain kind of, in infinite dimensions, we get certain anomaly. What is in what? Already in finite dimension, we can consider this twisted Durham complex, or maybe form of H bar, and we can tensor by a local system, consider like line bundle with regular singularity. Its connection and regular singularity. So we can twist by representation of fundamental group of my space to C star. It will be C star to kind of first Betti number of X. This cohomology we can twist by a local system, by this torus. And the situation that it says that in infinite dimensions we kind of do not know a priori which, maybe we twisted our things by some local system. So we should consider universal cohomology with all local systems. And this effect says that we kind of change the local system by which we twist the whole story. And what happens, you get new walls And if you cross these new walls, you change parameters in this torus. You change parameters of stores in some nonlinear way. And this is called 4D wall crossing in Gayoto-Murnetsky story. So at the end of the day, we get some kind of very general class of resurgent functions, which will happen the following. You will get some kind of maybe plenty of, let's say, stock sectors in H-plane. Then in stock sectors you get certain analytic function yi bar, which yi kind of element in a torus. Holomorphic functions which has some asymptotic expansion. It's 0. But now if you cross the wall, you make transformation something like this. Yi goes to yi multiplied by 1 plus exponents of roughly 1 over. You get transformations like this. So when h bars were close to 0, they are very almost constant. So you glue first such things, and you solve some Riemann-Hilbert problem. But then you consider its kind of other variables xi alpha, and they goes to which will be it will be parameters of C star local system, but now will be basis on cohomology, which I don't know, maybe xi alpha, and they will be changed by some formulas. Also, if you cross the walls, you multiply by variable y multiplied by exponential small terms, so it will be auxiliary variables. So the transfer will be linear in xi and non-linear in y. And this xi will have again some asymptotic expansions, which I think from conjecture that if we have these properties, then formal power series will be resurgent. You get infinite analytic, endless analytic continuation, all this. Yeah, 4D, 4D. Yeah, holomorphic bundle, some nonlinear manifold, vector bundle, some nonlinear manifold. Yeah. Yeah, and this story should be pretty general. It's not related only to the sectional functional. For example, here one can modify the one form of maybe an integrate differential of integral of some h of p t ut of t dt. You can add also some Hamiltonian to the action. H will be function on m cross c to c, some polynomial on two variables, and then if it's quadratic in momenta, then we go back to heat kernel. Yeah, so it's all these things really should be partial case of one big picture, and nothing is force us to do only one-dimensional field theory. One could do three-dimensional field theory. I think it's maybe arbitrary dimensional field theory. So this picture, which people call 2D, 4D, it's not really relevant. It's kind of this little bit general story valid for whatever quantum field theory which admits complexification. Okay, thank you.